This podcast is going to walk us through valence electrons and the octet rule, and sadly has nothing to do with hockey, but I couldn't resist giving you this beautiful stop on the skate. All right, so let's first start with talking about valence electrons. So valence electrons are the number of electrons in the outer shell. So think back to previously when we did our electron configurations and we said what was in the first energy level and second, the SP, D, and F blocks. So to determine that, and it wouldn't be a bad idea to label your periodic table, we look at the group number of the A block elements, and that tells us what the valence electrons are. So A block is working itself across, excluding the B block, which is your transition metals. So we have 1, 2, skip a few, 3, 4, 5, 6, 7, and 8. So 8 valence electrons is your maximum number of electrons. If you think about the S block, groups 1 and 2, and the P block, 3 through 8, that's 6 electrons and that's 2 electrons. The maximum you can get is 8. When you start to add in that D block, remember that's a lower energy level, so that's not the outer energy level. So all the fun stuff happens with those valence electrons. That's where your reactions are taking place. That's where compounds, both ionic compounds are transferring those outer electrons, covalent compounds are sharing those valence electrons. We can visualize those with electron dot structures. And bonding is going to be the joining of two atoms in a stable arrangement. This can be by gaining electrons or losing electrons, and those two are considered your ionic bonds, or by sharing electrons, which is your covalent bond. So we're not going to focus on covalent for this chapter. We are going to focus just on ionic. Would not hurt for us to have a quick overview, though, of those two bonds. So in an ionic bond, again, your key takeaway here is this is the full, ooh, I don't like that color. This is the transfer of electrons. So the metal gives up an electron to the non-metal. And what is special about the ionic bond is you are forming these charged elements. And it's actually those opposite charges that work like a magnet to pull those two atoms together. That's an electrostatic attraction. That's an ionic bond. It's incredibly strong. And in a covalent bond, we are sharing, that's a highlighter, we are sharing electrons. And so there's no transfer of electrons, but you have two nonmetals, or a nonmetal and a metalloid, and they are both agreeing to count that extra electron from the other element as one of their magic 8 for the octet rule. So they wind up being held together by this shared pair of electrons. So there's no transfer, which means there's no charges, because there isn't a transfer of electrons. So ionization energy helps us to explain the transfer of electrons. If you have a low ionization energy, like what we would see on the metal side of the periodic table, you are going to lose electrons because it's easy to take them from you. If you are on the non-metal side, you are going to gain electrons. It's not easy to take electrons from you. So this trend really explains why metals lose and why non-metals gain electrons. So the octet rule is a rule that elements follow. They want 8 electrons in the outer shell. They want to reach an octet in that outer shell. And for some elements, say if you have 7 electrons already there, it's easy just to gain an electron and you're at 8. And for other elements like our metals, they only have 1 in their outer shell. It's easier for them to give 1 away and drop to the previous noble gas stage or noble gas configuration. But really, it's all about what can I do to get to that magic number of 8? Am I going to lose, gain, or share electrons to reach a stable or noble gas configuration? Ions will form when elements try to reach an octet by gaining or losing electrons. So this is specific to ionic compounds, as we are forming ions or charged elements and particles. And again, we're only going to see this in ionic compounds, which are only between metals and nonmetals. As we said previously, ions are charged particles. So we can have positively charged particles. These elements have lost electrons. They have more protons now than electrons. We call them cations. And it is metals that are your cations. If you think about it, when we look at our charges, we have +1, +2, skip a few, +3, this is +2 or +4, -3, -2, -1, and no charge. So it's your metals that are willing to give up an electron. They have so few valence electrons, they give them up, they become cations. Anions are negatively charged ions. They're gaining electrons. For instance, fluorine has 7 valence electrons. It will gain 1 electron to reach the same configuration as neon, the noble gas right next door. And when it does take on 1 extra negative charge or electron, it takes on a negative charge overall. So these are your nonmetals that are gaining electrons to reach their octet. The group number will indicate the ionic charge. So we went through and labeled these. I would recommend labeling this on your periodic table as well. So let's take a look at how we would form a cation or an anion by looking at what the electron configuration is and talking about where those electrons are positioned. So let's use sodium for an example. Sodium is right here. So what I'm going to do is I'm going to start by writing the electron configuration for sodium. So 1s2, 2s2, 2p6, 3s1. So this is the electron configuration. It tells us how many electrons are in the first, second, and third energy level and what blocks that they're in. All right, so let's also think about how many electrons there are versus how many protons there are. Sodium has an atomic number of 11. That means it has, oh, that's tough to see. Let's try yellow. That means it has 11 positive charges, 4, 5, 6, 7, 8, 9, 10, 11. And when it's neutral, it also has 11 negative charges. So let's put that in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So normally these positive and negative charges would cancel each other out. You have 1 positive charge for every negative charge. It's neutral. It's happy. All right, let's look at what this would look like as an element. All right, sodium has 11 protons in the nucleus. Check. There's my nucleus. In the first energy level, I have 2 electrons. So I'm just going to represent those as dots. There's my 1s2. Done. In my second energy level, I have 2, let's see here. Let me highlight this in a little different color here. There's my second energy level. I have 8 total electrons. 2 of them are in the S block, 6 of them are in the P block. For our purposes, I'm just going to put them all 1, 2, 3, 4, 5, 6, 2, 4, 6, 7, 8. Okay, so there's 8 electrons here. Adding those up, we have a total of 10. We have a third energy level to deal with here. Here's our third energy level. And in my third energy level, I have 1 electron. Okay. If we were to look at the electron configuration, you would look to the very outer shell, the highest energy level, and you would say this has 1 valence electron. That matches what we said. I told you this matches the group A numbering, 1. This has 1 valence electron. If we were to draw this, it would look like that for a Lewis dot structure. Okay. Now, we have 2 things that can happen here. First, that electron, I could find a nonmetal willing to give up 7 valence electrons, so I could have 8. Or, and this is going to be the right answer, I could just give away that outer shell one. If I give away that outer shell electron, okay, if this goes away, I now have 8 in my outer shell. That whole energy level goes away. We lose that electron to a nonmetal. And now we have the same configuration as the previous noble gas. It's stable. Okay, if we were to lose one electron, all of these are going to cancel except for one. That leaves us with an overall positive 1 charge. We know that metals like sodium lose electrons, they become cations. And I totally forgot to mention the way I like to remember cations versus anions. Cations has the word cat in it, and cats are positive. You're welcome. Anions are like onions, they're negative. I got nothing else. All right, so let's work this the opposite way with a nonmetal. Let's talk about oxygen. I want to do that in red. Oxygen. We're going to write oxygen. Let's see, where is oxygen on the periodic table? Oh, right there. That's what we're working with. And oxygen, we're going to write the electron configurations. So 1s2, 2s2, 2p4. Perfect. All right, and I'm going to do an accounting for all the protons and all of the electrons. So this is atomic number 8, which means it has 8 protons. 1, 2, 3, 4, 5, 6, 7, 8. And a neutral oxygen also has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that's neutral. All right, let's draw this out and see how this plays out. So in my nucleus, I have 8 protons. In the first energy level, okay, looking right up here, first energy level, I have 2 valence electrons. 1, 2. Done. Second energy level, I have 6 altogether. 1, 2, 3, 4, 5, 6. Okay, so what this looks like is a Lewis dot structure, 2, 3, 4, 5, 6, is we have a spot for 2 more electrons before we get to our magic number of 8. Now, oxygen is further to the right and higher up on the periodic table, which means it has a higher ionization energy. It's going to take a lot of energy to remove an electron. And it's a nonmetal, which means it will gain electrons to get to that noble gas configuration. So what's going to happen instead is it's going to find a nonmetal to give it 2 more valence electrons. Okay, and when that happens, we change this to 6. And we are going to add 1, 2 more valence electrons to our total count. So these are all going to cancel, leaving us with a -2 charge. And thinking back to how you labeled your periodic table, we know that everything in the oxygen family has a 2- charge because it's only 2 electrons away from having a stable octet. They will all gain 2 electrons to get to a stable octet. All right, just want to highlight again that we have charges that should be labeled on your periodic table. These show some of the ionic states. We'll go through this in a later podcast. This should say right here, this should be +2 or +4. So these have varying charges for the carbon family. One thing to keep in mind, and I'm sure you've seen this a bajillion times, especially if you've taken chemistry before, is that elements by themselves have certain properties. So for example, this is a bad color to write in. This is sodium metal. Sodium metal is very reactive with water. It's very explosive. It's not something you want to have around. This is chlorine gas. Chlorine gas is toxic. It will kill you if you inhale it. These are 2 very dangerous things. When they become chemically combined in an ionic compound, they form sodium chloride, and they're the most delicious seasoning that you have on your table. That's just table salt. And the way they are able to form is exactly what we talked about. This one valence electron from sodium, the metal, is donated to chlorine. And when it loses an electron, sodium takes on a positive 1 charge. Oops. And when chlorine accepts that electron, it takes on a negative 1 charge. So that transfer electrons creates that positive and negative charge that's holding those two elements together, and you have a new compound with new physical properties. Arranged perfectly, if you were to look at the lattice structure, all your positive charges are touching negative charges. You would never have two positive charges touching or two negative charges touching. And it creates this beautiful crystalline structure.